Hi, my name is Dr. Jerry and I welcome you all to Era of Knowledge. Today I'm going to start a new lecture on set theory. In this lecture we'll see the complete analysis of sets, so let's begin. Before that, subscribe our channel for more updates and don't forget to hit the bell icon. In our mathematical language, everything in this universe, whether living or non-living, is called an object. If we consider a collection of objects given in such a way that it is possible to tell beyond doubt whether given object is in the collection under consideration or not, then such a collection of objects is called a well-defined collection of objects. Now we need to know what a set is in reality. Well, the definition of the set is a well-defined collection of objects. By well-defined collection of objects, it means that we can definitely decide whether a given particular object belongs to a given collection or not. The objects, elements and members of a set are synonymous terms. For example, the set of intelligent students in a class is, option A, a null set, option B, a well-defined collection, option C, a finite set, option D, not a well-defined collection. The solution is option D, since the criterion for determining the intelligence of a student may vary from person to person, so this is not a well-defined collection of objects. Let's look at another example. Which of the following is the collection of first 5 prime numbers? Option A, 1 2 3 5 7, option B, 2 3 5 7 11, option C, 3 5 7 11 13, option D, 1 2 3 4 5. The solution is option B. It is clear that first 5 prime numbers are 2 3 5 7 11. Let's see the notations of sets. Sets are usually denoted by capital letters and their elements by small letters. Let P be any set of objects and let N be a member of P. Then we write like this, and read it as N belongs to P. If N is not an object of P, then we write like this, and read as N doesn't belong to P. A set is often represented in one of the following two forms. Number 1, roster form or tabular form. Number 2, set builder form. In roster form or tabular form, a set is described by listing its elements, separated by commas, within braces. For example, the set of months of a year which have 30 days, in roster form can be described as April, June, September, November, within braces. Let's take another example. The roster form of the following set. Option A, 369, option B, 159, option C, 139, option D, 239. Answer is option C. Since x is a positive integer and a divisor of 9, so x can take values 139, so roster form of the set P is 139, within braces. In set builder form, instead of listing all the elements of a set, we describe the set by some special properties satisfied by all of its elements and write it as Q equals x such that P of x holds, or x such that x has the property P of x, and read it as A is the set of all elements of x such that x has the property P. These symbols stands for such that. For example, if set Q equals 1 2 3 4, then it can be written in set builder form as option A, Q equals x such that x belongs to N and x less than or equal to 5. Option B, Q equals x such that x belongs to N and x is less than 5. Option C, Q equals x such that x belongs to N and 1 less than x less than 5. Option D, Q equals x such that x belongs to N and x is less than 4. The answer is option B. Clearly, Q equals x such that x belongs to N and x is less than 5. Describes the set Q equals 1 2 3 4. A set which does not contain any element is called an empty set, or null set, or void set, and is denoted by phi, or void braces. Problem 1. The set x such that x belongs to N and 3 is less than x is less than 4 is equal to option A, set containing 3 and 4, option B, set containing only 4, option C, phi, option D, set containing only 3. The answer is option C, since x belongs to the set of natural number and 3 is less than x is less than 4, so the given set has no element. Problem 2. The set x such that x squared plus 1 is equal to 0 and x belongs to the set of real number is equal to option A, minus 1 1, option B, 1, option C, minus 1, option D, phi. The answer is option D. We know that there is no real number x such that x squared plus 1 is equal to 0. Remember, this is not a null set, as it contains one element. A set which has at least one element is called a non-empty set. A set consisting of only one element is called a singleton set. For example, a set X such that X belongs to the set of natural number and 2 less than X less than 4 is a singleton set, since X belongs to the set of natural number and 2 less than X less than 4 implies that X equals 3. A set which is empty or having a definite number of elements is called a finite set. For example, a set X such that X belongs to the set of natural number and 1 less than equal to X less than equal to 10 is a finite set, since elements of the given set are first 10 natural numbers. The given set is a finite set. The number of distinct elements contained in a finite set A is called its cardinal number and is denoted by n of A. For example, if A equals 1, 3, 5, 7, then n of A equals 4. Another example, the number of elements in the following set is 5. A set which is not finite is called an infinite set. In other words, a set in which the process of counting of elements doesn't come to an end is called an infinite set. For example, a set of all points in a plane is infinite set, as all the points in a plane cannot be counted. Two sets, P and Q, are said to be equal if every element of P is also an element of Q, and every element of Q is also an element of P. In mathematical language, if X belongs to P, implies that X belongs to Q, and Y belongs to Q implies that Y belongs to P, then P and Q are equal sets and we can write P equals Q. For example, the set X equals a set of -2 - 1 and set Y equals a set of T such that T denotes the roots of the equation T squared plus 3T plus 2 is equal to 0. Equivalent sets, if the cardinal number of two finite sets P and Q are equal, then these two finite sets are said to be equivalent. Mathematically, if n of P equals n of Q, then P and Q are two equivalent sets. Clearly, equal sets are equivalent, but equivalent sets need not to be equal. For example, the set 1, 2, 3, 4, 5 is equivalent to X such that X belongs to all vowels, as the cardinal number of the both sets are 5. Subset and superset. The set B is said to be subset of set A if every element of set B is also an element of set A. Symbolically, we write it as or, where A is superset of B. Remember, to show that two sets A and B are equal, show that A is a subset of B and B is a subset of A, then A equals B. If B is a subset of A, then A is a superset of B. Let's take an example. The set A equals 1, 2, 3 is the subset of set 1, 2, 3, 7, 8. And the set 1, 2, 3, 7, 8 is the superset of set A. Proper subset. The set B is said to be a proper subset of set A if every element of set B is an element of A, whereas every element of A is not an element of B. We write it as and read it as B is a proper subset of A. Observe that every set is a subset of itself, but not a proper subset. B is a proper subset of A if every element of B is an element of A, and there is at least one element in A which is not in B. For example, the set 1, 2 is the proper subset of the set 1, 2, 3. Power set. The set formed by all the subsets of a given set A is called the power set of A. It is usually denoted by P of A. Suppose set A equals 1, 2, 3, then the power set of A equals set of null set of 1, set of 2, set of 3, set of 1, 2. Set of 2, 3, set of 3, 1, set of 1, 2, 3. The null set and the given set are always two subsets of the given set. Notice, if a finite set A having n elements, the cardinality of the power set of set A is 2 to the power n. Let's see how. The number of ways we can select no element from set A is nc0, which is null set. We can select one element in nc1 ways. Two elements can be selected in nc2 ways. Similarly, moving forward, all elements can be selected ncn ways. So clearly, the number of ways of selecting elements from set A is the cardinal number of the power set of A. The total number of ways equals 2 to the power n, as we already know this formula. That's it for today. In the upcoming lectures we'll be learning Venn diagram, operations on sets, laws of algebra of sets, formulae to solve practical problems of sets.